Okay, we go on with polynomial equations, and here we consider symmetric polynomials and an expand extension to the idea of Vieta formula. We had considered Vieta formula previously, in a video earlier on where we looked at the possibility of dealing with polynomials without explicitly solving them, but by just working with the sum and product of their roots. Okay, so let's move on. Yeah. So the goal of this lesson will be to revisit Vieta's formulas for higher degree polynomials. So back then we consider Vieta's formula for basically quadratic equations, quadratic polynomials, that is. I think we looked at third degree a bit, but we didn't do so much with it. But we really went all out about quadratics. So, and then we also work systematically with symmetric sums of roots, especially for cubic and quartic polynomials. Then we'll solve simple problems using only sums and products of roots, no explicit solving for the roots. And that's the essence of the Vieta formula. Okay, so setup and notation, first of all. So consider a polynomial of degree n. I mean, we have seen this several times, that P of x is an x raised to power n plus an minus 1 x raised to power n minus 1 plus all of that plus a1x plus a naught with complex roots r1 r2 up to rn counted with multiplicity. In the last video, we considered the uh the fundamental theorem of algebra, which tells us that if you have a non-constant polynomial of degree n, then it has exactly n complex roots counting multiplicity. Also noting that real roots are subsets of complex roots. Okay, so in this case, we have the idea coming up again that if we have this polynomial of degree n with complex roots r1 up to rn counted with multiplicity, then we can say that p of x is a sub n into x minus r1, x minus r2 up to x minus rn, like that. Then we define the elementary symmetric sums of roots. So the following are called the elementary symmetric sums of roots. First of all, we have the first step, the first stage, which is the sum of all the roots directly. That's r1 plus r2 up to rn. Okay, and then for E2 now, E2, we then multiply them in pairs. So we have summation uh, from I less than or equal to I less than or equal to j less than or equal to n. We have all the possibilities of R1 and RJ, Ri and RJ rather. So it means you have R1, R2. So, and you want to guarantee that I I is always less than or equal to 1 is always less than or equal to I. That means that I can be equal to 1 or greater than 1, right? Then I is always less than J, and J can be less than or equal to N. So that means so if we have 4 now, so it means we have summation of R1 plus, so we have R1, R2 plus R1, R3 plus R1, R4 plus R2, R3 plus R3, R4, like that, okay? And then we have at the third level now. So we multiply them in triples. So we have R1, R2, R3 plus R2, R3, R4, plus, every possibility of picking them in threes. And then for EN now we have it up to, we have R1, R2, Rn, everything multiplied together like that. For order two, that's simple, that's very easy. For order two, we just have R1 plus R2. That's what we have right here. So there's no need for E2 in that case, because we just okay, I mean, yeah, all we have for E2 and EN will just be the same there, because it just be R1 times R2, that's alpha times beta. So for quadratic, right? E1 is alpha plus beta, E2 is alpha times beta. So if you now take alpha and beta as R1 and R2, that's when we have R1 plus R2, and then E2, which coincides with EN, will just be alpha R1 times R2, or alpha beta, right? So these are the elementary symmetric sums of the roots. Okay, taken having taken care of that idea now, so we look at the general Vieta's formulas of degree n. I mean, we've considered it for degree 2. So let the p of x be equal to this polynomial, which have roots r1 to rn. Then we say that the polynomial of x, p of x, is actually the leading coefficient an uh multiplied by the product of all x minus ri's, starting from x equals 1 to n, and this exactly the same statement with this. So this is exactly the same. So this thing that looks like pi is basically saying just like what we have for sum, just like all this sum now, say sum of all ri's. That means ri plus r1 plus r2 plus r3 up to rn. But this means uh, product of all x minus ri. So that means x into r1 into x minus r2 up to x minus rn. So by expanding, we actually get the Vieta's relationships, the Vieta's relation that is E1 now. When we expand this, so it tells us that E1 is equal to summation from I equals 1 to n of Ri, and that would be minus an minus 1 all over an, minus an minus 1 all over an. So it's like when we have a quadratic, that's where we have minus b over a normally. So, because it's going to be like AB. So this is going to be like minus B over A. And RIRJ, in that case, is usually C over A. That's like the constant all over A. So, but in this case now, we have E2, which is RIRJ. RIRJ equals AN minus 2 over AN. E3 is RIRJ, summation of all RIRJ, RK, which is minus AN minus 3. So you see, it's following a pattern. So we have minus AN minus 1 over N. Next, we have AN minus 2 over N. Then the signs are alternating, minus plus minus now. For 3, E3, we have AN minus 3 over AN. And then up to N, now we have R1 times R2 up to Rn equals minus 1 raised to power N. All right. So if N is odd, then we are going to have negative. So you can see 1 and 3 are negative, but even, that's 2. So we have positive, positive like that. So when N is even, we have minus 1 raised by any even number is going to be 1. So that's positive. So and that is A naught over AN. And this one coincides in the case of quadratic. Now this coincides with what we usually have as C over A in that case. So the signs alternate, like you can see minus plus, and so on and so forth. So that's the general Vieta's formulas. So for order 2, I think we did it the other time, that we just consider, okay, I guess let me just show that so that we can then imagine that kind of a thing if you want to solve. I mean, if you're looking at higher orders like this. So what this is telling us is that if you have a quadratic polynomial ax squared plus bx plus c, right? So we're simply saying that p of x can be written as a into all the product of, there are two roots here, x minus r1 into x minus r2. So I think we dealt with that already. So here, so we have this in this form. So if we now go ahead and say this is the same thing as a into, if you expand this now, x times x squared minus x times minus r2, that's x minus r2, xr minus xr2 minus r1 times x, that is minus xr1, then minus r1 times minus r2, that's r1 r2 easily. So we have the px here still. So p of x now is equal to a into, if you have this now, x squared minus, so you see x is common, so you have r1 plus r2x, plus r1 r2, like that. That's what is happening there. So this is the same thing as a, all the that thing that looks like pi now, a from I equals 1 to 2 of x minus ri. So it's exactly the same thing. So here now we have p of x to be equal to ax squared minus, okay, that's ax squared minus a into r1 plus r2x plus a r1 r2. So we have this now. So since it's the same p of x rather, we can then compare 10 by 10. So this is a and this is a, right? So then b now is simply just going to be, so if you compare, so b, okay, this is x now. So it means b is going to be equal to minus a r1 plus r2. Okay, so we say b is equal to minus a into r1 plus r2, meaning that if you want r1 minus r1 r2, that means r1 plus r2 rather is equal to minus b over a. That means you divide through by minus a. So we have minus b over a. On the other hand, now you see that the constant c is simply equal to a r1 r2. Okay, so we see that c is a r1 r2. In this case, we need r1 r2, so you divide through by a. So you have r1 r2 is equal to c over a. So that's basically the idea of the Vieta's formula, that without knowing explicitly the roots, you can know that the sum of the roots is minus b over a. So you can express the sum of the roots in terms of the coefficients of the polynomial, and the product of the roots is also c over a in that case. So this one only looks a bit more complicated because we're talking about higher degrees. So we have generalization for these things now. That's exactly what this is about. So let's look at some special cases. Some special cases like quadratic, cubic, and quartic. First of all, quadratic. Oh, that's what I just did over there, interestingly. So for quadratic, we have let x squared plus bx plus c equals 0 have roots r1, r2. So in this case now, we don't care about the coefficients of we don't the coefficient of x squared is taken to be 1. So in that case now, r1 plus r2, which would have been minus b over a, is now minus b over 1. So that's minus b. r1, r2 is simply the constant. So if you go cubic, so we're only considering this whole thing for monic polynomials, meaning polynomials that have 1 as the coefficient of the highest exponent. Okay, so in that case now, so we're not, so here I did I used ax squared and all that. So but what we are doing now is just sorry, is this is the general form. So what we are doing is just x squared. We now say ax plus b. Okay, we shift it because the coefficient of x squared here is taken to be 1. So that's what is happening now. So if we do that, we then have so we have, instead of minus b over a, we have minus b over 1, which is minus b. Instead of r1, r2, r1 plus r2 is supposed to be minus b over a. That's minus b over 1. That is minus b. R1, R2 is C over A. That is C over 1 here. That's C. Now, if you go cubic, that's higher order now, which we are really here for. So for the cubic nomic type, we have x cubed plus ax squared plus bx plus c equals 0. Normally, if you're not doing it nomic, if it's not nomic, if the coefficient of x cubed is a, for instance, that would have been ax cubed plus bx squared plus cx plus d equals 0. But here now, we are taking the coefficient of x cubed to be 1. But we are assuming that we have divided through by a, or something like that. So in this case now, because it is cubic, we expected that it is going to have roots r1, r2, and r3. That's following the fundamental theorem of algebra, that this polynomial of degree 3 is going to have exactly 3 roots. Then we can say that r1 plus r2 plus r3 will be this a now. It's now be minus a over 1. We have that. Then we now take them in pairs. r1, r2 plus r1, r3 plus r2, r3. This is the application of this e2 here now. So first of all, add them together in ones. E2, multiply them in pairs and add together. E3, multiply them in triples and add together, and so on and so forth. That's exactly what we have here too. So because you have 3 roots, you have r1 plus r2 plus r3, that's minus a. Then for the e2 now, that's r1, r2 plus r1, r3 plus r2, r3 equals b. So normally it should have been b over a, but it's b now. So negative, positive. Now the next has to be negative. Then multiply them in threes. So you have r1, r2, r3 equals minus c. And that's what you have right there. So very easy to follow. If you go quartic, for instance, see what happens. So if you go degree 4, that means the highest power of x is 4. And then we take the nomic case where the coefficient of x raised to the power 4 is just 1, like what we have right here. So we now have x raised to the power 4 plus ax raised to the power 3 plus bx squared plus cx plus d equals 0. So, and because it is of order 4, of degree 4 now, we have roots r1, r2, r3, and r4. Then we can say that r1 plus r2 plus r3 plus r4 is minus a. Then you multiply in pairs now. So you have r1, r2 plus r1, r3 plus r1, r4 plus r2, r3 plus r3, r4 is equal to b. And all of that now is what has been summarized in this case. Summation for every I less than j of ri, rj. Then we also multiply in threes. So you see minus a, b, minus c, d, and it goes on like that. So for E3 now, we have R1, R2, R3 plus R1, R2, R4 plus R2, R3, R4. And that is equal to minus C. And then you multiply all the 4, and that is going to give you D. So minus A plus B minus C plus D. And that's how it goes for quartic. Okay, so then we have, we are talking about symmetric polynomials and Vieta extension now. So let's see the idea of symmetric polynomials in the roots now. All right. So we have try to fit this as much as I can. So a symmetric polynomial in R1, R2 up to Rn is a polynomial expression that does not change when we permute the roots. So for a cubic with roots R1, R2, R3, examples of symmetric expressions include R1 plus R2 plus R3. So anyhow you do it, whether R1, R2 comes first or R3 comes last, it doesn't matter. Then R1 times R2 plus R1, R3 plus R2, R3, we can say that's symmetric. Anyhow you do it, you get the same result. Or R1 squared plus R2 squared plus R3 squared is all the same. So anyhow you sum up, you get the same result because a symmetric polynomial in the roots is a polynomial expression that does not change when we permute the roots. So if you switch the roots anyhow you like it, you still have the same answer. If you call R1 R3 or I mean if you put the roots, if anyhow you arrange the roots, you get the same results with all these things. So R1 R2 squared plus R2 minus R3, R1 minus R2 all squared plus R2 minus R3 all squared plus R3 minus R1 all squared. These are all symmetric. So a non-example will be this because this should not be symmetric by itself, like R1 squared R2. But this won't be correct in this case. But the cyclic sum will now be R1. So this is not symmetric on its own, but because you are doing the same with all the roots. So like you have R1 squared R2 plus R2 squared R3 plus R3 squared R1. This is now symmetric. Okay. So the key fact is you use as a tool, not proved here. So you can use it as a tool. Any symmetric polynomial in R1 up to Rn can be expressed as a polynomial in E1, E2, or En. So you already know E1 is when you sum the roots one by one. Then E2 when you multiply the roots in two by two and then sum together. En is when you multiply the roots n by n and sum together. All right. So since each EK can be written in terms of the coefficients via Vieta, we can evaluate symmetric expressions using only the coefficients. So it means that whenever you have this kind of expressions, you can actually evaluate them, in terms of the coefficients A, B, C, and D, because for instance, we already know for a cubic polynomial R1 plus R2 plus R3 is simply plus A, that's A. Then R1 R2 plus R1 R3 plus R2 R3 is equal to minus B. Whereas R1 R2 R3, okay, that doesn't come up here. So I mean, and when you square this now, we can find a way of factoring this, and then when we factor it, then we can then express them in terms of the coefficients. So let's look at some useful identities for symmetric sums. So let's see what we can do with this. So useful identities for symmetric sums. So for roots R1 up to Rn and elementary sums EK, sum of squares for any n greater than or equal to 2 can be written as summation from I equals n is R1 squared equals, so R1 squared, that'll be equal to E1 squared minus 2E2. Okay? So that is a very important expression. And if you look at it properly, everything seems to be following a pattern. So for n greater than or equal to 3, for sum of cubes now. So summation from I equals 1 to n of the cube of the sum of the cube of the roots now. That's R1 cube plus R2 cube plus R3 cube and so on and so forth. Gives us E1 cube minus 3E1 E2 plus 3E3. Then for a cubic, which is n equals 3 now. So we have the summation from over I less than or equal to I less than or equal 1 less than or equal to I less than j less than or equal to 3 of Ri squared Rj squared multiplied by Rj squared, that is equal to E squared minus 2E1 E3. So for reciprocals, assuming no root is 0, of course, if we assume that we don't have a 0 root, so for degree n now, summation from I equals 1 to n of the reciprocals of the roots will be En minus 1 all over En. Okay, so it means that if you get up to if you have a cubic polynomial now, so you're going to have it means this expression 1 over R1 is going to be E2 all over E3. So for pairwise reciprocals now. So that is you have 1 over R1 R2 plus 1 over R1 R3 plus 1 over R2 R3 like that. It becomes an minus 2 over n. So these are very useful identities. Now we talk about symmetric polynomials in this case. So let's look at some worked examples to drive home the point we've been trying to make all this while. So, worked examples. Example one, we talk about a cubic situation. Like, so you have sum of squares of roots now. So imagine P of x is x cubed minus 6x squared plus 11x minus 6. This looks familiar. I think we've done this using factorization before now. Okay. So of course, this is going to have 3 roots because it is cubic. So let this have roots R1, R2, R3. So use Vieta to find R1 plus R2 plus R3. Then R1, R2 plus R1, R3 plus R2, R3, then R1, R2, R3. Now, these ones are easy because the first one is simply just going to be minus A. And A in this case, don't forget, if you assume that since this is the coefficient of x cube is 1, so this is our A, this is B, this is C. So the first one is simply just going to be minus A, that's minus 6. So this one is going to be 6. Then this one, of course, is going to be B. And B here is 11. So this is going to be 11. R1, R2, R3 is going to be minus C. That's minus 6, which is also 6. Then this one now we now need to compute it. Okay. So let's look at the solution. So solution here, we compare x cubed minus 6x squared plus 11x minus 6 to x cubed plus ax squared plus bx plus c, just like what I did. So a is minus 6, b is 11, and c is minus 6, like what we have here. So for Vieta, okay, that's the American way to pronounce it, I believe. So for Vieta, we have R1 plus R2 plus R3, that's minus a, like I said, which is minus 6, and that is 6. Then R1 R2 plus R1 R3 plus R2 R3 is equal to b, which is equal to 11. 11 is B. R1, R2, R3 will be minus C. That's minus 6, and that is 6. Now, if we use this idea now to take care, so we want to now compute R1 squared plus R2 squared plus R3 squared. So whenever you have a situation like this, so the first thing we need to do is to forget about the R1 squared plus R2 squared plus R3 squared first. Just forget about it and then just do R1 plus R2 plus R3, which you already know, and square it. So once you square this now, but the square of this is going to be, of course, you're going to have R1 squared, then R1 R2, R1 R3, and so on and so forth. And then at the end of the day, by the time you work all of that out, you're going to have R1 squared plus R2 squared plus R3 squared into 2 into R1 R2 plus R2 R3 plus R2 R3. R1 R3 plus R2 R3. So that simply means that this is what you're looking for. So you're looking for R1 squared plus R2 squared. So you can make this the subject of formula. So at the end of the day, if you transfer this now, so if you keep this here, so it means you have R1 plus R2 plus R3 all squared minus 2 into R1 R2 plus R1 R3. 2 into R1 R2 plus R1 R3 plus R2 R3. So we can then substitute, since we know this is now, this is what we are looking for. So R1 plus R2 plus R3, we already found that to be 6. That'll be 6 squared minus 2 into R1 R2 plus R1 R3 plus R2 R3. That's 11. So we have 36 minus 22, which is 14. So that helps us. So we see that the answer is that R1 is R1 squared plus R2 squared plus R3 squared is 14, like that. So without solving for the actual roots, we can actually do this like that. And of course, maybe you want to, okay, well, do we have to verify anything here? Yeah, there's no point. Yeah, I mean, if we get the actual roots, we can square them. Okay, I feel like we can test this out, right? What's the expression again? X cube, we have x cube minus 6x squared plus 11x minus 6. So I'll just use graphical method to see if we can get, if they all have real solutions. I go to decimals as usual. So I come here, so I'm doing x raised to power 3, okay, minus 6x squared. You can also use Wolfram Alpha like I did in one of the previous videos. 11x, I think it's under data fitting. Okay, now here we have the 3 solutions. They are all real, interestingly. So we have x to be equal to 1. Then the next one is x equals 2. And the next one is x equals 3. Okay, so that's sweet. So thankfully, all the solutions are real. So Do you want to check this now? Do you want to see how correct everything we've been doing has been? Let's see. So R1 plus R2 plus R3, that's 1 plus 2 plus 3, that's 6. Then R1 R2, that's 1 times 2, that's 2, plus R1 R3, that's 1 times 3, 3, plus R2 R3, that's 2 times 3, 6. That's 2 plus 3 plus 6, 11. Correct. Then R1 R2 R3, that's 1 times 2 times 3, which is also 6. Now we have R1 squared, R1 squared plus R2 squared plus R3 squared. That will simply be 1 squared plus 2 squared plus 3 squared. That's 1 plus 4 plus 9, right? So 1 plus 4, 4 plus 9 is simply 14. So everything is fine, okay? So you see, we are not just working with something that is not correct. So this works perfectly. So now look at example 2, where we in a cubic situation. I think what we did before is also was cubic too. So what about sum of reciprocals of roots? So for the same polynomial x cubed minus 6x squared plus 11x minus 6 equals 0, with roots R1, R2, R3. Note the constant term is not equal to 0. So this is minus 6 now. So no root is 0. So if we have a constant, if there's no constant term, then of course you're going to have a 0 root. So this is safe. So if you check this and there's nothing, there's constant here, then it means no root is going to be 0 at all. So what we now want to do is to compute 1 over R1 plus 1 over R2 plus 1 over R3. Of course, since I know the answer, so I know 1 over 1 plus 1 over 2 plus 1 over 3 is the solution. LCM there is 6. So I have 1 in 6, 6. 6 times 1, 6. 2 in 6, 3. 3 times 1, 3. Plus 3 in 6, 2. 2 times 1 is 2. So that's 6 plus 3, 9 plus 2. That's 11 over 6. That's what this answer is going to be, because we know the actual solutions to be x equals 1, x equals 1, x equals 3, like we saw on the graph. So let's look at the solution, how it should be done now. So you have 1 over R1 plus 1 over R2 plus 1 over R3. So the LCM is R1, R2, R3. So R1 in R1, R2, R3 is R2, R3. R2 in R1, R2, R3 is R1, R3. R3 in R1, R2, R3 is R1, R2. So if you put this whole thing together, this is E2 now. E2 is that's clearly B, that's positive B. And then E3 is minus C. Okay, that's the negative of the constant. So E2 we already know to be 11. E3 we know to be 6. So it means this is simply 11 over 6. And that's correct with the original roots we actually know. Okay. So we go for another cubic. Here now it says, okay, we are still dealing with the same thing. So again, for the polynomial x cubed minus 6x squared plus 11x minus 6 equals 0, with roots R1, R2, R3, we want to find R1, R2 squared plus R1, R3 squared plus R2, R3 squared. So, I mean, once you see each of them squared like this, so the best way to go is just forget about the original thing and go for this kind of thing. We start with the identity R1, R2 plus R1, R3 plus R2, R3 square. So when you square them like this and you expand everything, so you're going to have you're going to have for sure R1, R2 squared. You're going to have the square of each one times then 2 into R1, R2, R3 into R1 plus R2 plus R3. So that's the easy way that will go. You're going to have, for instance, you're going to have R1 squared, R2, R3. So this is common now. So, and from here, you see, this is what you need. All right, this is what you need. So you can say this one now is equal to this whole thing squared minus 2 times all this squared. So that's simply in terms of E1, E2, E3 now. You see this guy, this is E2. So we have, because if you are looking for this now, it will be this squared minus this whole thing, 2 times all this. So this expression now is this one. This is E2 squared minus 2 times this is E3 into E1. So that means E squared minus 2E1 E3. So for example, one, E1 is 6, E2 is 11, and E3 is 6. We found this already. Thus, you can then say this whole expression is simply E2 squared. E2 is 11. That's 11 squared minus 2 times 6 times 6. That's 121 minus 72, which is 49. So the answer is simply 49. Of course, if you want to try it using the actual solutions, so the first one is going to be 1 squared, 2 squared. 1 squared, 2 squared is simply 4. The next one will be 1 squared, 3 squared. That'll be 9. The last one will be 2 squared, 3 squared. That's 4 times 9, 36. So 36 plus 13 is 49. That works. So we go quartic now. For quartic, we have sums of squares and products. So let P of x be x raised to power 4 minus 3x cube plus 5x squared minus 7x plus c. So now A is minus 3, B is 5, C is minus 7, and D is 2. All right. And they have roots. That has roots R1, R2, R3, and R4. Okay. So we now want to find all this. Of course, this is easy. And then we go ahead and compute this. We have also done this before. So this one is simply going to be minus 3, okay? And this is going to be 5. And this next one is going to be minus 7, that's 7. And the last one is going to be minus 2, easily. I mean, it's going to be just 2, sorry. I think it's just 2. Yeah, so that's it. So the solution, just like I've explained, is compare the the expression you have with the standard form in a monic situation where the coefficient of x4 is not a. So you shift the a to the other side. So you have this. So a is minus 3, b is 5, c is minus 7, d is 2. So E1 now, which is R1 plus R2 plus R3 plus R4 is minus a. That's minus 3, which is 3. E2 is simply b, which is 5. E3 is, the signs alternate. So minus plus minus plus. So E3 is minus 7, that's 7. E4 is simply positive plus 2, that's 2 right there. So for the sum of squares, now, which we now need. So you see, we need R1 squared plus R2 squared plus R3 squared plus R4 squared. So instead of worrying about that first, what you just do is just square this whole thing. So you have R1 plus R2 plus R3 plus R4 squared, and that is going to be equal to R1 squared, the sum of all R1 squared plus 2 times the sum of the pairs, the pair like that. So generally speaking, so what you now need is this expression. So sum of all Ri squared is equal to this one, which is E1 squared minus 2 times E2. So you can then substitute. You already have E1, E2. So E1 squared, E1 is 3, so you have 3 squared minus 2 times E2, that's 2 times 5, which is 10. So 9 minus 10 is minus 1. So if you put all of that together, you get minus 1. Then for E1 is 3, so that means the answer E1 is 3, E2 is 5, E3 is 7, and E4 is 2. And then R1 squared plus R2 squared plus R3 squared plus R4 squared is minus 1 easily. And then if you do another quartic, talking about reciprocals and pairwise reciprocals, so you have x raised to power 4. I think it's the same expression. Yeah, it's the same expression, yeah. So for the same quartic, x raised to power 4 minus 3x cubed plus 5x squared minus 7x plus 2 equals 0, which roots R1, R2, R3, R4. We want to compute this and then compute this. What do? The solution, we recall the general identities. So recall the general identities. So for single reciprocal like this, it's just En minus 1 all over En. Then for what is this called now? For pairwise reciprocals now, that's summation of 1 over RJ. So just remember En minus 2 over En. Here we know n is 4. So for the reciprocals now, we simply have E3 over 7, and then of course E4 over 7. And then for some of pairwise reciprocals, we have E2 over E4 because we have E4 minus 2 over E4 like this. So, and we know these things. So E3 we already know is 7. Okay, E3 is 7. So 3572 in short. Okay, so E3 is 7 and then E4 is 2. Then again, E2 is 5 and E4 is 2. So the answers are simply 7 over 2 over 5 over 2. So if you just know the identities, then it makes things pretty easy. Okay, so imagine general strategy for symmetric expressions like we've been doing now tells us, given a polynomial P of x with roots R1 up to Rn, identify the expression in the roots you want and check it is symmetric. That is, it is unchanged under permutation of Ri. Okay? Then we write the expression using algebraic identities in terms of elementary symmetric sums. I know the elementary symmetric sums. Add the sums one after the other. That's E1. E2, multiply the roots in pairs and add them together. And then E3, multiply the roots in triples and add them together, and so on and so forth. You can then replace EK by the expressions and coefficients using Vieta, like E1 is minus AN minus 1 over AN, E2 is AN minus 2 over AN, then EN is minus 1 raised per N, A naught over AN. Then simplify to get a numerical value or a simpler expression in the coefficients like that. Okay. Then this avoids solving the equation for the roots explicitly. So the whole idea of symmetric polynomials and Vieta is simply telling us that you don't have to solve a polynomial to be able to do whatever else you need to do. Okay. Um, is this what we just did now? This cubic, x cubed plus 4x squared. Is that what we just did now? If otherwise, I would like to handle it. Yeah, I think it's different. So I'll try to answer. Okay, let's go through all the questions first. Then I'll answer question one and we'll call it a day. So as far as this is concerned, so practice questions now. Uh no solving required. I mean, that's important. That's what Vieta is about. So all can be solved purely using Vieta's formula and symmetric sums. So the roots of x cubed plus 4x squared plus 5x minus 2 is equal to 0 are A, B, and C. So if the roots are A, B, and C, or you can also say alpha, beta, gamma if you like. So we are looking for A plus B plus C. That is actually the first elementary sum. Then 2, we have AB plus BC plus CA. That's the second elementary sum, E2. Then 3, we need ABC. That's the third elementary sum, E3. And then we now need A squared plus B squared plus C squared. And then we have that hint there that A plus B, A plus B plus C, AB plus BC plus CA first, then the identity of the sum of squares, of course. So because we need we need the first three, or the first two, in fact, to answer the fourth one. So, but before I do that, let's look at the second question. Let x cubed minus 2x squared plus 3x minus 4 be 0. Have roots P, Q, R. So you have P cube, Q cube, R cube. So we need to compute this. So we have been given a simple way. All you just need to do is to identify E1, which is 2, that's minus minus 2. E2 is simply 3, and E3 is minus minus 4, which is 4. So you have 2, 3, 4. So you can then just put this in here and you're good to go. That's for 2. For 3, yeah, we have a quartic case. We need symmetric sums and reciprocals. So just like what we've done, just not long ago. Then for quartic, we want to do mixed symmetric expression. You have mixed symmetric expression. So you have that for question 4 now. So you have this whole thing, and you want to compute this symmetric quantity. So you can expand. You have R1, R3 plus R1, R4 plus R2, R3 plus R2, R4. That's like E2 right there. That's in pairs. So you need to use E1, E2, and all that to do the computation. And then, of course, this expansion. Okay, this one has even been solved and all that. So you have all of these things going. So you can have a cleaner trick like this. And but an easier symmetric way is this other one. But I mean, you can just try your hands on that. And then we have question 5 finally. Question 5, you have a cyclic symmetric expression where you let x cubed plus 3x squared minus 2x plus 5 is 0, having roots A, B, C, and then you need so you want to use Vieta to show that A plus B plus C is minus 3. Of course, that's clear from here, minus 3. Then AB plus AC plus BC is simply minus 2. That's plus minus 2, which is minus 2. ABC is minus 5 straight up. So use the identity for cubics. So we now want to get this cubic. So you have the identity. So you just slot in there and move on. Okay, let's answer this question 1, and we round it off with that. So the question is, we have the cubic expression, the cubic polynomial x cubed plus 4x squared, right? Plus 5x minus 2 equals 0. So the roots of this are A, B, and C. So we now need to compute, number 1, A plus B plus C. That is simply E1. E1 we already always know. Mm, okay. Yeah, let me just write what we need to compute first. So I think it's always very good to get everything in order first. The roots of this are A, comma B, comma C, right? So if we say this is now, let's say we now need to compare. So we compare x raised to power 3 plus 4x squared plus 5x minus 2 equals 0. We compare that with, say, so since the roots are already ABC, I think I want to use something else. Maybe I want to use PQR. So we have x cubed plus px squared plus qx minus r equals 0. So this implies that p is equal to 4, then q is equal to 5, and r, okay, this R should actually be positive. So now we can say R is equal to minus 2. So the sign is important. So, and we know, um, number one, to find, to find A plus B plus C. That's E1 in short. That's simply E1. So we know E1 is just the first one is negative. So that's minus P. Okay? That's minus P. And that is simply minus 4. Easily. Then number two, we need to find AB plus BC plus CA. That is simply E2. Okay? And we know E2 now it's going to be plus Q. Okay, that's plus Q. Q is 5. So we have this is simply 5. That's easy peasy. And then we have 3. We want to find ABC. Okay, to find ABC. ABC is simply E3, right? ABC is E3. So, and we know E3 is simply minus R, okay? So R on its own is minus 2. So we have minus 2, which is simply 2. So E3 is equal to 2. So we have that established. Then, having taken care of that, we need the last one now. So the fourth thing now is to find number 4, to now find A squared plus B squared plus C squared. So we don't have to worry. Just go ahead and do A plus B plus C all squared. That's going to be A plus B plus C into A plus B plus C. Of course, it has a shorter formula. I can easily state, but I mean, in case you're just coming across it and you don't know the formula, just do the regular thing. A times A is A squared, A times B is AB, A times C is AC. And then next you have B times A. That's another AB. B times C. That is BC. So I'm arranging it like this so I can tidy things up very easily later. Then if you go for C, so C times A is AC. So you have AC right here. So I'm aligning this together. So C times A is AC. C times B is BC. So I have BC right here. Then C times C is C squared. Oh, okay. I think I've jumped. Let me start again. So A times A is A squared. A times B is AB. A times C is AC. Good. Then next, I have B times A is AB. Okay, like this. B times A is AB. Then B times B is B squared. So I have B squared here, you know. Then B times C is BC. So I just put it all over the place so I can tidy up easily later. Then I have C times A is AC. Okay, I think I want to change this. C times A is AC. Then C times B is BC. Then C times C is C squared, like that. So we can then say that A plus B plus C all squared is equal to A squared plus B squared plus C squared, which we are really looking for. And then for the other ones, we have, for the other ones, we have AB and AB. That's 2AB plus AC and AC, 2AC, BC and BC, we have 2BC. Okay, so that means that we have A plus B plus C all squared is equal to A squared plus B squared plus C squared plus 2 into AB plus AC plus BC. So this is what we are looking for, like I said. So you can transfer this to the other side. So we have A plus B plus C all squared minus 2 into AB plus AC plus BC, and that is equal to A squared plus B squared plus C squared, which you are really looking for. So you can say, so A squared plus B squared plus C squared is equal to A plus B plus C all squared minus 2 into AB plus AC plus BC. Okay, so A plus B plus C, we found that already. A plus B plus C, we found it already to be equal to E1, okay? That's E1. So that means this is simply E1 squared minus 2 AB plus AC plus BC. That is E2. Yeah, that's E2, which is here, E2 here. So the other one is E1. So we have 2E2, 2E2. Now the issue is what are the values? E1, like we found, is 5. No, E1 is minus 4. E2 is 5. Minus 4 and 5. Okay. So we have minus 4 squared minus 2 into 5. So minus 4 squared is 16. 2 times 5 is 10. Okay. And that is equal to 6. So we can say, therefore, A squared plus B squared plus C squared is equal to 6. And that is the result. Well, if you are curious and you really want to go graphical to find what exactly the solution should have been, all I just need to do is just say x cubed plus 4x squared plus 4x squared plus 5x plus 5x minus 2 minus 2. Oh, okay. So we have only one real root. The other ones are imaginary. So let's not bother ourselves. So we just move on with that. So you see, you may not know the roots, but you can find their sum, their products, and things like that. Yeah, and with this, we come to the end of this very interesting video talking about symmetric polynomials and Vieta extension. And that simply tells us that without knowing the actual solutions to a polynomial, you can actually find the sum of the polynomials, and you can also express some symmetric expressions out of that. All right, so with this, I come to the very end of this video. Thank you so much for listening. Let me know how helpful this is for you. And if you have something else you'd like me to try out, feel free to let me know. If you have subscribed already, I must thank you very, very much for doing that. And if you have not subscribed, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Yeah, right. Having done that, of course, you can also become a member of the channel by clicking on join. So join makes you a member of the channel, and it gives you some special privileges, as you will see there. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.